Hello, welcome back. Time for it to get a little bit more challenging here as we go away from binary compounds into compounds that contain more than two different elements. So this particular one's sort of an introduction to polyatomic ions. So I'm going to start off by giving you a little bit of review on what a polyatomic ion is and why they exist. And then we'll kind of get into some of the naming parts that go along with this. I'll probably break this into a couple videos as well. So polyatomic ions, in terms of what these things are. So polyatomic ions are sort of an interesting in-between, between ionic and covalent. They do a little bit of both. And so remember that what atoms are trying to do when they start to bond together is they're trying to achieve stability, right? They're trying to get that full outer energy level of electrons, kind of like what we talked about in one of the previous videos. And in this particular case, they end up doing sort of a combination of things. And these particular polyatomic ions were discovered later, which is why they have some kind of funky names to them and some different things that we have to do to deal with them. But these are all about another pathway that atoms can use to achieve some stability. So I'm going to use the example of chlorate is the one that I'm going to use for right now, CHLORATE, as a good example of a polyatomic ion. So a polyatomic ion is exactly what it sounds like. It's an ion, so it has a charge, right? And it's made of several atoms, polyatomic ions, right? Chlorate is Cl, chlorine, right? Also has oxygens, and it turns out it has 3 oxygens to them. And this thing functions all together as a team with a charge of -1. That doesn't mean each atom has a charge of -1. That means the group, the team, has a charge of -1. And that's what chlorate actually is. So if you want to think about what this is, imagine there's a chlorine atom in the middle, and then there's going to be an oxygen, another oxygen, and then there's going to be another oxygen like that. And this whole set all together functions like it has a charge. That's what makes it a polyatomic ion, as opposed to chloride, right, which is just this, right? Chloride is a single anion, as opposed to chlorate is a polyatomic ion. They function as a team. So why do they do this? So I'll remind you about valence electrons and kind of some memory about what this is. Now, I'm not testing you on this at all, but in terms of wondering kind of why these have the formulas and some of those things that they have, here's just a little bit of background into it. So imagine chlorine. If you remember where chlorine is on the periodic table, I'm going to get my pen back here. Chlorine on the periodic table is over in the halogens end. It's over on one of the nonmetals, so there it is like that. And chlorine has, to start with, 7 valence electrons. Again, why is that? It's because it's element number 17. It's got 2 electrons in its first energy level, 8 in its second energy level, and 3 in its third energy level. But again, I'm not testing you on this. Just kind of dig back into your Chem 1 brain that you knew this once upon a time. So there's chlorine, looks like that. Oxygen, similarly, looks like this, where it had 6. 1, 2, 3, 4, 5, 6, or something along those lines. And again, it's because it's at element number 8. So it's got 2 electrons in its first shell and 6 electrons in esse second shell. And so when these things start to bond together, they kind of form this team, right? There's chlorine can be there, and an oxygen can kind of come up and start to bond like that. So again, this is a Lewis dot structure. Again, you've drawn these maybe in Chem 1, but I'm sure it's been a little while. And this right here is that shared pair between them. And that shared pair right there is also known as a covalent bond. That chlorine and that oxygen are starting to form a molecule. But it's not quite happy yet, right? Because chlorine doesn't have quite all that it needs. So it has another oxygen can come up and bond like this. And again, when it does that, we've got a second bond right there. And then we could have a third oxygen come up, say up here. 1, 2, 3, 4, 5, 6. I'm doing it in the different colors just so you can kind of see what it is. And so we've got a third bond. So now we have 1, 2, 3 covalent bonds. So this is almost like a molecule, right? It's fairly stable. But if you take a look at chlorine, chlorine is almost happy, right? In order to be stable, the magic number is 8 for every element other than hydrogen and helium. So for these, it's almost stable as a molecule, but not quite. If there was just one more electron, this would be a perfect structure. And so what has happened is that somewhere in chlorine's past and its associations, it's going to pick up that electron from something else that's happy to get rid of it. And if you take a look at this structure right now, this structure is stable. It's like a molecule. But as soon as I put this extra thing on there now, it's not a molecule anymore. It's an ion. And this whole thing has a charge because it needed one extra electron to fill it. It has a charge of -1. And so again, polyatomic ions are just these sort of molecules that form. They're almost always formed from two nonmetals, almost always. But we can't name it like a type 3 compound because it is still an ion. And this ion can then now magnetically, ionically bond to other ions, like, for example, sodium. And you could form sodium chlorate. It's actually a pretty common little salt that can form because this is a 1+, this is a 1-. Opposites will attract. And when these two bond together, they're bonding together ionically. So polyatomic ions do both covalent bonding inside their little molecular team structure, but then they will also do ionic bonding to other things because opposites attract. This is kind of the magic, joy, despair that is known as polyatomic ions. Just to give you, again, a little bit of background on what it is, because it may make this next part a little bit less frustrating if you know that there's basis to it. Again, I'm not going to test you at all on doing Lewis dot structures, but when we're trying to figure out some of these different patterns, knowing that there's at least a reason for why these patterns are there sometimes will help. So a lot of our polyatomic ions fall into this category that are called oxyanions. And in fact, chlorate is an oxyanion. So what does that term mean? Well, these are polyatomic ions. They're anions, which means they're negative, and they have oxygen in them. Almost half of our polyatomic ions are technically oxyanions. So like chlorine and oxygen together is an oxyanion. But rather than coming up with a chlorine trioxygenate, some crazy name to it, there's a system that they've invented to try to make naming of these very common polyatomic ions a little bit easier. And this is the 8-ite thing that I'm going to kind of go through right here. So the first one to know is ATE. ATE is what we use with oxyanions to indicate it's the most common form. Form. So this one, for example, was called CHLOR, but not chloride, right? This is chloride, like that. This one is chlorate, ATE, CHLORATE, CHLORIDE. So the name tells you that it's a polyatomic. Having that ATE or the ITE ending, I'll show you in a second, tells you that there's a polyatomic in there. It's not just a binary regular anion. So the ATE tells you it's the most common form. And so there's few of these that you do need to kind of learn to recognize. They're not uncommon at all. So here's our set of these. We've got ClO3 chlorate. We've got nitrate, NO3. We've got carbonate, CO3, which is a 2- charge. That's a 3. We've got sulfate, SO4, which is a 2- charge. We've got phosphate, PO4, which is a 3- charge. What else we got? We're missing a couple. I'm missing, which one am I missing? Hold on. I got nitrate. I got chlorate. I got, what else? Sulfate, phosphate, chromate. CrO4 2-. I may have missed another one, but close enough. All of these are very common molecular ions, polyatomic ions. And every one of these you can see is an oxyanion. So their names are the root, whatever that nonmetal is, and 8 after it. Chromate's the unusual one that there's a metal in there. So this is chlorate, nitrate, carbonate, sulfate, phosphate right here, and chromate. I feel like I'm missing one. But anyway, a couple things that are really frustrating about these is that there's kind of some things that doesn't feel like there's patterns, like the charge. There's no particular pattern to which ones are 1- and 2-. It's related to that Lewis dot structure thing, but without drawing them all out, you're not going to see it. So you kind of have to memorize or just be ready to deal with it. And by the way, if you don't have this sheet out, that's the Chem 2 common polyatomic ions. It's the reference that I put in that module. You should probably get that out. It'll certainly help when you're following along. So anyway, like I said, number one, no particular pattern for charges. They can have a variety of charges. And then number two, there's not an obvious pattern for whether there's 3 oxygens or 4 oxygens. The ATE is simply reserved for the most common form of that oxyanion, regardless of how many oxygens there is. So that's why sometimes there's 3 and sometimes 4. The next thing that came along is the ITE form. It turns out that a lot of these have more than one possible team structure that works. So there's another version of chlorine and oxygen that can form a polyatomic ion. The most common form is called chlorate. The second most common form is called chlorite. And luckily for us, there is a pattern here. One less oxygen. Always. Whenever the chlorite or the ITE form exists, and it doesn't always, not every polyatomic ion has this, but when it does exist, it always has one less oxygen. So if chlorate is ClO3, chlorite is ClO2, and it's still a 1- charge. By the way, there's no difference between writing 1- just as a negative sign versus as the 1-. So if I do that back and forth, you're welcome to do that as well. Nitrates, very similar. If nitrate is NO3, then we know what nitrite is, NO2, 1-. Again, they don't all exist. So this is carbonate, CO3, but this, CO2, that's not carbonite. That doesn't exist, even Star Wars fans. This is just carbon dioxide. It does not form an ion when it does that. So that one just doesn't exist. Sulfate does exist, and it's sulfite, SO3, 2-. So the couple of things to realize about the ITE versus the ATE form. Again, the biggest difference is one less oxygen. It's always -1. And number 2, the charge does not change. So that's super helpful that you don't have to have a new set of charges to it. So if it's a 1- here, it's still a 1-. So that's really, really useful. All right, I'm going to kind of erase over, give myself a little bit more room. It turns out that certain families can have even more than that. And that's where this per and this hypo come in. The one that really does this better than any other is chlorate and the chlorate family. So there's a couple of other examples where some of these do come up as well. So we've got right here on our board, chlorate and chlorite. It turns out they've discovered later on there were indeed some additional forms of this, like 2 wasn't enough. Thanks, chemistry. So CHLORATE, that tells me that's the most common form, CHLORITE. Well, it turns out there's also this one, ClO, just a single oxygen, one more or less. So this one is kind of like chlorite, but it's even below chlorite, and the name tells you this, hypochlorite. ITE. So again, this part stays the same, but now we've added the prefix hypo on there to say it's even below chlorite. There's chlorite and then there's below chlorite, hypochlorite. Hypochlorite's, by the way, a really common polyatomic ion found in bleach. Sodium hypochlorite is what the household name for bleach is. And then it turns out that there's also a case where you've got one more oxygen, ClO4, 1-. Notice these all have the same charge. This is +1 oxygen. Well, in this particular case, the +1 oxygen, we use a different prefix on there, and it's perchlorate, CHLORATE, perchlorate. Chlorate is still the most common one, and chlorite is still slightly less common than that, 1 less oxygen. So hypo means 2 less, and per and ATE, because it's 1 above the chlorate form. Perchlorate, by the way, is really found in rocket fuel. Haha, there's some fun stuff right there. So perchlorates, really, really nasty reactive things. So ate and ite are the 2 most common forms. Ate is by far the most common. Ite means 1 less oxygen. And in the rare cases that there's even an extended set of oxyanions, you might have a per and ate, which means 1 more oxygen, or hypo and ite, which means even 1 less. So again, that pattern, that naming system of ate, ite, per, and hypo still works. And so if I can write, per and ate would be the most, ate would be the most common. This would be the most oxygens. Ite would be -1 oxygen, and hypo and ite would be the least number of oxygens. So again, this one right here is the base form, the ate form, ATE form, and all the other ones are named as plus or minus from there. So again, a lot of these have them, some don't, some do, but when you're looking at the names, that's one of the big things that changes. Okay, one little quick periodic table pattern with these. Which ones form our ions? So we've already kind of visited a couple of these. We've got nitrate, we've got carbonate. You can't have oxygenate because it's just oxygen. Fluorate could exist, but it generally does not for some reasons because of fluorine is a jerk. But you can have phosphate and sulfate and chlorate we've discussed, right? There's those ones that we've already talked about. And then we also have chromate over here, and I'm going to put this one over here. So there's kind of our common ATE forms that we have. So carbonate, nitrate, phosphate, sulfate, chlorate, chromate, and then this one right here is permanganate. There it is. Permanganate's a little bit weird because there is no manganate. It's just a permanganate. I don't think they realized the number of oxygens was going to be different when they named it. So it's got an old holdover name. It's kind of annoying. But permanganate and then chromate over here. So there's chromate with chromium. Permanganate is this one. Carbonate, nitrate, phosphate, sulfate, and chlorate. So a couple of things to identify here in terms of numbers of oxygens. And this is the one that you may like if you remember this pattern. If you're trying to remember the number of O's, like, how do I figure this out? Okay, here's the pattern. If it is here to here, all of those have 3 oxygens when they're in their 8 form. So carbonate, nitrate, and chlorate all have 3 oxygens. I'm not talking about the charge here, I'm just talking about the number of oxygens. Anywhere else, and they will have 4 oxygens in the 8 form. So you've got CrO4, you've got MnO4, you've got PO4, and SO4. I haven't put the charges up here. But again, anywhere else, if they're in this outside band right here, that little number 7 shape, those are going to have 3 oxygens to them. And if they're anywhere else on the periodic table in an oxyanion, they're going to have 4 oxygens with them. It's a pretty good way to remember how many they've got just by physical location on the periodic table. Again, charge, I have not put charge in here because there's no great pattern on charge. And so now why am I talking about anywhere else? Well, because I'll talk on this in a later video. There are some other ones down here that do form oxyanions, and I will teach you how to write the names and formulas for those in a later video. So this is the major overview of oxyanions, kind of what they are, what a polyatomic ion is just in general, and our main oxyanion families. Again, chlorate's the one that shows us all 4 of the ATE, ITE variations. We've talked about now what ate and ite are, that there may be a per or a hypo occasionally shows up from time to time. And then we talked about a strategy for remembering the number of oxygens. This outside band right here has 7 oxygens as oxyanions, anions, and all of the other ones have 4 oxygens. So there you go. I'll see you in the next one where we'll talk about some more of the exceptions and some of the other types of polyatomic ions that are out there. Hope you liked it.